Hello everyone, my name is Sanditya Larope Sutanto from Universitas Indonesia. Now I will talk about signal propagation and channel models. So let's start with propagation characteristics. So propagation characteristics itself can be described as how the signal propagates from transmitter to receiver. And there are path loss, shadowing, and multi-path fading, which are unpredictable. So as you can see here from the graph, the y-axis represent the power received since the transmitted power is constant, and the x-axis depends on the distance between the transmitter and receiver. So the blue line here, as you can see, if the distance increases, the power received will decreases exponentially, while the red line shows a changing intensity of the power received. And of course, in changing the changing in received power experiences, power must have some kind of ripple effects. So these scenarios, this blue is path loss, the red one is shadowing, and the green one is multipath fading. So that's why it is so unpredictable. Okay, how to solve it? So there is a method called path loss modeling, and there are actually many solutions like Maxwell equation, free space and two-path models, ray tracing models, single slope path loss exponent model, and measurement-based and standard models. So let's talk about the Maxwell equations. So the Maxwell equations investigates the interaction between the electric field and magnetic field, which is combined together to become electromagnetic propagation. However, it comes with a drawback that it is difficult and impractical. Thus, simpler methods needs to be used, which are the next one, the free space and two-path models that we will talk in the next slide. Okay, so let's start with a free space model or the LOS model. So the free space models describes the propagation of signal without any obstructions to the receiver, such as curvature of Earth or maybe some buildings. And in general, the power falls off is inversely proportional to the distance squared, and it is proportional to the wavelength squared. And then there are two-ray models. So two-ray model, the receiver receives two types of signals, LOS and non-LOS. Non-LOS signal came from reflection or refractions. And so in this model, the power falls off is proportional to distance squared and distance powered by 4. And it is independent of the wavelength, unlike the previous model. And then there is a general ray tracing solution. So this model signal components as particles. So there's reflection, scattering, diffraction. It requires site geometry and dielectric properties. So it is easier than Maxwell because it is geometry, unlike the Maxwell, which is differential equations. And then let's see the next slide, the simplified path loss model. So it is used when path loss is dominated by reflection. And so this model is actually the simplification version of path loss model. So gamma here is the most important parameter for the path loss exponent, and it is determined empirically. Gamma itself, in this case, ranges from 2 to 8. And the DR is the receiver location, the D is reference point to the receiver location, and PR is the received power, and PT is the transmitted power. Okay, so what's the big deal in MM wave? MM wave is located in a high spectrum bandwidth range. And as you can see here in the image, it starts from the top left, which are the lowest frequency spectrum, to the highest frequency spectrum in the bottom right. So from top left to the bottom right. And in this case, this is the case in United States. And as you can see, the 5G is allocated in the 38 gigahertz spectrum. But the wave itself actually starts from 60 gigahertz to 100 gigahertz. See, so it works in higher frequency. And of course, that means it is easier to get bandwidth. But actually, this millimeter wave the wave is actually still in research. Like right now, 5G is not even implemented in the whole world yet, but wave is better than 5G. So it can be said that it is still immature. The channel models is still immature, and it actually has oxygen and rain absorption, which can be an obstruction. And then, so how can the problem be solved? Well, it can actually be solved using what is called as empirical channel model. So in area which are not suitable for wave, the existing channel modeling cannot be used. And early cellular empirical models are based actually on extensive measurement, and the examples includes Okumura model, Hatta model, COS231 model, and multi-slope model. And then the disadvantage that comes with the empirical model is that it is dependent on the location of the experiment. There are many obstructions that can happen or can be disturb the wave, such as buildings or if we take in geography factor and etc. So that's all for the propagation characteristics and channel modeling. I hope it can help you guys, and please consider dropping a like if you find this video to be helpful, and you can comment down below also. Thank you very much.